Hi everyone, this is Devasattam and you are watching the third lecture of EE 635, Applied Linear Algebra. This would be the first module. So I hope you are enjoying these video lectures. Please share your suggestions, if you have any complaints or questions by posting comments either on YouTube or uh, in the Google Classroom platform. And also please keep logging into Google Classroom for regular updates on the course. Okay, so now let us proceed with the content of lecture 3. Let me try and share my screen here. Okay, I hope the screen is visible. All right, so let us have a very quick recall of what we have been doing, right? So we were trying to solve this systems of linear equations, right, which we were writing as Ax equal to b. We would like to obtain all solutions of a system like Ax equal to b. What we realized in lecture 2 was the following, that one can do so by exploiting this fact that equivalent systems have exactly same solution sets. Right? Now, let me remind you what we mean by equivalent systems. So we have seen that there is this idea called linear combinations of equations, right? So then if we have two systems, system 1 and system 2, system 1 has several equations, system 2 has several equations, then system 1 and system 2 would be called equivalent to each other if the following happens. Then if every equation, listen carefully, every equation in system 1 is a linear combination of equations in system 2, and every equation in system 2 in turn is a linear combination of equations in system 1. Then we say that system 1 and system 2 are equivalent systems. So then we have realized that equivalent systems will have exactly the same set of same set of solutions, right? So if a point is a solution for system 1, then it will also be a solution to system 2 if system 1 and system 2 are equivalent, and vice versa, right? Now, that's all good, but the question is, how do we obtain equivalent systems? We have seen that to obtain those equivalent systems, how to get those linear combinations carefully. The idea is that if we have an equation Ax equal to b, then from here, if we obtain Max equals Mb, where M is a square invertible matrix, right? Then if this is system 1 and this is system 2, then system 1 and system 2 are equivalent. Yeah, that's the trick. And then we didn't stop here actually. We actually showed that how one can generate these matrices M by doing the so-called elementary row operations. And we found out that products of elementary row operations are good candidates for these invertible M matrices. So how does one get these M matrices? M matrices are typically products of elementary row operation matrices, right? And we have seen that there are three such elementary row operations. One is substituting a row by a non-zero multiple of that row, then adding substituting a row by the row plus a multiple of another row, and then thirdly, permutation of rows, right? These are the three elementary row operation matrices. And then we found out that with elementary row operation matrices, one can convert a matrix into a so-called row reduced reduced echelon form, right? The idea is the following: how does this solve? How does this help us solving a given system of linear equations, right? The idea is that if we are given a system of linear equations, and then if we can convert that system into another equivalent system, so the solution set will remain the same because it's equivalent. But now, if it is in row reduced echelon form, we will see that it's absolutely simple to get the solution, right? Because row reduced echelon form are such that from there one can directly read off the solution. All the solutions, in fact, not just one solution. In fact, the whole solution set can be described by just looking at its row reduced echelon form. How to understand this would be the subject matter of this module, right? I believe that the best way of doing this, best way of understanding this, so this RRE form is the one that we have been calling, we have been alluding to as the easy to solve form, easy to solve equivalent system, right? So this is, so I believe the best way of understanding why this RRE form is easy to solve is by going through an example, right? That is what I'm going to try and do, yeah? So please bear with me. Let me do this calculation for you. So for us, I have already kept these equations with me. Let me, for the time being, not put these right-hand sides. Instead, let me put all zeros. So this becomes a homogeneous system of equations. This will be instructive, illustrative enough. In the later module, we will see how to tackle the situation when there are right-hand sides also, and there is this non-zero B vector on the right-hand side. Yeah. Okay. So let us try and see how this works out. Okay. I'm going to write this first as matrix. Yeah. So what is this matrix here? This matrix is going to be, the coefficient matrix is going to be 1 and 2 and a 5 and a 1. Then a 2, then a 3, then 9 and 4, then 3, then 7, then 14, then 2. This is my 3 cross 4 matrix. So I'm going to write that this is a matrix in R3 by 4. I'm going to perform row operations on it to convert this matrix into its row reduced echelon form. Okay, so what was the method we discussed in the last lecture? Then start scanning from the first row, start scanning from the left. So we start scanning the first row from the left. We already get a 1 here, which is non-zero. And therefore we can take it as a leading term, and it's already 1, so I don't have to make it 1 anymore. So this already is 1, so this I can take as the so-called pivot, right? So this is my pivot. With this pivot, what I'm going to do is I'm going to do the following row operation. So the first row operation is going to be replace row number 2 by row number 2 minus 2 times row number 1. What does that result in? Well, this keeps the first row intact, doesn't change. But the second row minus 2 times the first row. So this is going to be 0. This is going to be 3 minus 4, which is minus 1. Then it's going to be 9 minus 10, which is minus 1. Then it's going to be 4 minus 2, which is plus 2, right? I hope I'm okay. I did this correctly. So I had 2, 3, 9, 4 minus 2, 4, 10, and 2. So 3 minus 4 is minus 1. 9 minus 10 is minus 1. 4 minus 2 is 2. Good. So you're right. So this is going to be 3, 7, 14, and 2. This is after the first row operation. The second row operation, once again, I'm going to take this guy as pivot. So so recall that for row reduced echelon form, the leading one, wherever it appears, whichever column it appears in, every entry in that column must go to 0. So that is what we're trying to do. We've already made this second entry in that first column equal to 0. Now we have to make the third entry also equal to 0. That's why I've taken this one as again a pivot. I'm going to substitute R3, row 3 by row 3 minus 3 times row 1. Let's see what happens. This is going to be unchanged, 1, 2, 5, 1. Of course, this is 0, minus 1, and 2. This, of course, will become 0 now. Then it will be 7 minus 6, right? That is plus 1. Then I have 14 minus 15, right? Which happens to be minus 1. And then I have 2 minus 3, which is a minus 1 again, right? I hope I haven't made a mistake. So I'm substituting row 3 by row 3 minus 3 times row 1. So that is 0 here. And 7 minus 6, then 14 minus 15. So that is minus 1. Then 2 minus 3, which happens to be once again minus 1. Very good. And now this is the form, right? Now I scan, so I have already made this leading one here. I have made leading one appear here, and then I have made sure that every other entry in that column is 0. So now I come to second row, and once again I start scanning from the left. I see a 0, so I leave it. Then I see a minus 1. So this is a leading term. This I have to make 1. So what do? I substitute row number 2 by row number 2 divided by minus 1. Yeah, so that it becomes 1. The leading term becomes 1. So I have 1, 2, 5, 1. And then I have 0 and a plus 1, minus 2, 0, 1, minus 1, minus 1. This is what I have. Right? Now, the moment I have leading 1, I have to make the other entries in the column to be 0. What are those other entries? This is 1 and this is 1. These two entries I have to make 0. So how do I make these two entries 0? Well, of course, I change row 1 by row 1 minus 2 times row 2. And then I'm going to do this in one shot. So I'm going to change, but I don't encourage that. For you, you should try it step by step. I also change R3 by R3 minus R2. Okay, see what happens. With this now, this one will not change anymore because these are zeros. Yeah, that's the benefit of making these guys 0. I mean, the other entries in the column where a leading one appears, I have to make them 0. That's the reason why. When I do this further changes, the leading ones don't change anymore. Once the leading ones are created, they are there. Now, with this guy becomes 0, of course. Then I have 5 minus 2, which is 3. And then I have 1 plus 4. So 1 plus 4 happens to be 5. I hope I have not made a mistake here. 2 minus 4, yeah, it's correct. This, of course, is 0, 1, 1, minus 2. This doesn't change. This is 0. This guy is going to become 0 because I'm doing R3 minus R2. This will be minus 1, minus 2. And this will be minus 1 and plus 2, which is plus 1. Right? I think it's okay. So I'm done. I've created these two zeros. So I'm good with this column. Now what do I do? Now, so this row is also done, the second row. Now I have to concentrate on the third row. And once again, start scanning from the left. So if I start scanning from the left, I get a 0 here, fine. I get 0 here, if I leave. This is the first leading term, yeah? And this leading term, I have to make 1. So what do? I change row number 3 by row number 3 divided by minus 2. This, of course, produces 1, 0, 3, and 5. 0, 1, 1, minus 2, and then 0, 0, 1, minus half. This is what it produces. Okay, and of course now this guy would be my leading term. If this guy is the leading term, then with this, now I have to make this guy 0 and this guy 0, right? So let us try and do that. Of course, so what changes should I do? I should replace row 1 by row 1 minus 3 times row 3, and I should replace row 2 by row 2 minus row 1. Sorry, row 2 minus um, row 3. This is the row operation that I must do. This happens to be 1, 0. This will become 0. What will this guy become? This is 3 times. So this is minus 3 by 2 and subtract. So this is going to be 5 plus 3 by 2, which happens to be 13 by 2. 5 plus 3 by 2. Yeah, that's 13 by 2. This is 0, 1. This ought to be 0. And what am I doing? I'm just subtracting. So this is minus 2 plus half. Minus 2 plus half happens to be minus 2 plus half happens to be minus 1.5, which is minus 3 by 2. This is 0, this is 0, this is 1, and this guy is minus half. Yeah, is that all right? So this is what we have. Now this is in row reduced echelon form, as you can see. This is a leading one, this is a leading one, this is a leading one. K1 here is equal to 1, K2 here is equal to 2, and K3 here is equal to 3, right? Now, once I have this, what does this really mean? It means the following. It means the following. This system of equations and this system of equations, what is that? So this system of equations, this is going to be my system 2. That's given by x1 plus 0 times x2 plus 0 times x3 plus 13 by 2 times x4 equals 0. x2 plus 0 times, okay, sorry, let me write it properly. Yeah, 0 times x1 plus x2 plus 0 times x3 minus 3 by 2 times x4 equals 0. And finally, 0 times x1 plus 0 times x2 plus x3 minus half into x4 equals 0. This system of equations and the earlier system 1, that is the given system of equations, they are equivalent because they have been obtained by taking linear combinations which are invertible, because I've done row operations only. Yeah, but now what is so good about this system 2? You see, for system 2, I know that each equation is like this one. So this is x1 plus just 13 by 2 x4, yeah, which implies x1 must be equal to minus 13 by 2 x4. Second equation is just x2 plus, sorry, yeah, it's a minus 3 by 2 x4 equals 0, which implies x2 must be equal to 3 by 2 x4. And similarly, the last one is x3 minus half times x4 equals 0, which implies x2 must be equal to half times x4, which means if I now choose x4 to be equal to u, which can be anything, any real number, then I have my solutions ready-made. The solution would be x1 must be equal to minus 13 by 2u, x2 must be equal to 3 by 2u, and x3 must be equal to half times u. So every solution is of this form, then every solution must be of the form, okay, hang on, every solution must be of the form minus 13 by 2u, then 3 by 2u, then half u, and then u, where u is any arbitrary real number. That's it. That describes all the solutions. And that is precisely what happens when we convert a matrix into its row reduced echelon form. That is precisely what happens. So coming back to the general case. Yeah, coming back to the general case. Well, you see, I mean, there could be some silly mistakes, silly calculation mistakes in between while I was obtaining the row reduced echelon form. I hope there is no mistake, but there could be some mistakes, but you understand the idea. That is what is important. So here, I hope there is no mistake though. Let's see. But see, when we convert something into a row reduced echelon form, yeah, as far as it's a homogeneous equation, what we get is the following. See, all the non-zero rows, so notice the following, that all the non-zero rows have only one of xki's, right? For each non-zero row. So for the first non-zero row, for example, so for example, row 1 will have xk1, yeah, and bunch of others, and those others will not contain any k1, k2, k3 at all. Similarly, row number 2 will have xk2, and this will continue till row number r, yeah, that is the final non-zero row. This will have xkr, and in these equations also equations contain one of xki's, and other variables must necessarily come with index from, notice carefully, this set gamma, which is defined as 1, 2, 3, dot, 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 up to n. These were my variables, x1, x2, x3, yeah. So the indices are 1, 2, 3 up to n. But in those equations now, these numbers will not appear. In the first equation, xk1 and things from gamma. In the second equation, k2 and things from gamma. Yeah, and then in equation x3, there will be xk3 and indices from this gamma, like that. Okay, so then notice what happens. So with these two observations, notice that equation 1 becomes, in the system 2, we have xk1 plus this summation. Looks profound, but trust me, this is nothing. I from the set gamma, some constants c1i, and then xi is equal to 0. So this I is coming from this gamma, which means those k1 up to kr don't appear here. Yeah, like there, like in the example that we created, provided the RRE was okay, notice that the first equation in system 2, the first equation has x1, where 1 is k1, and then x4 only. 2, 3 don't appear, x2, x3 don't appear. Second one has x2 only, and then once again x4, no x1, x2, x1 and x3. Here only x3 and x4, and no x1 and x2. That's what we are saying. So here the gamma set is just 4. So I hope you understand what's going on here. Similarly, equation 2 now will be, equation 2 will be xk2 plus summation I in gamma c2I xi equals 0. And this will continue, and I'll have the final non-zero equation will be I once again in gamma c r I x I equals 0. Yeah, so then we just define u1 up to un minus r as xi I in gamma. We get our solution as the solution becomes xk1 equals summation minus sine I in gamma sorry I equal to 1 to n minus r c1I. Yeah. Okay, sorry, there's no need. C I in gamma c1I xi. You can replace these xi's by u1, u2 up to un minus r and so on. xkr equals summation minus I in gamma c r I xi. That's it. Yeah. And these xi's are free to be chosen as u1 up to un minus r. That's it. So that's why we say that row reduced echelon form is easy to solve. And that is how we solve these equations. Okay. Now, before we move on to the next module, where we'll see some amazing consequences of this observation, yeah, one of the most important theorems in linear algebra will show up there. Yeah? But before we move on to module number 2, I want you to solve some problems, like our immediate attention problems and our homework problems. You know the definition. Immediate attention means that you have to do it right now before you move on to module number 2. Homework is something that can take some time. So look at this first immediate attention problem. This problem that we just solved, yeah. For that, find out the matrix M, the elementary row operation matrix is the product of the elementary row operation matrices that we convert the system into RRE, and verify that it is indeed it does its job by doing direct matrix multiplication. So that's your immediate attention problem number 1. Immediate attention problem number 2 would be to carry out this RRE business for this particular system of equations with the right hand side here. So I'm sure you'll be able to do that. And then these two are homework problems. Here you're going to write the solution set for the problem that we just solved, but in a more sophisticated form, matrix vector multiplication form. We'll see the meaning and implication of that in a later lecture, but this will be extremely important for us. So for you to be able to write the solution like this. Yeah, so you are the free variables of, in this case, use size would be just 1 because it was just only one independent variable we had. And this R will be a matrix of size. It has 1 column and 4 number of rows because there were 4 variables. So try and find out this matrix and do this description. Yeah. If you face any difficulty, of course, let me know, but try this out. Okay. So this dot often, so let me explain what this dot is. Dot is often when we don't know the exact size of some vector or a matrix, exact dimension we don't know, we keep it vague by putting this dot there. Okay, that's convention. Okay, and homework number 2 is describe all 2 by 2 row reduced echelon matrices. Okay, try these problems and then we'll come back to the remaining part of lecture 3. We'll start with module number 2 of lecture 3 and then we'll see how far we can go. Okay, yeah, so let us meet in some time for lecture number for module number 2 of lecture 3. Okay.